Hey, this is the video that I said I'd create on launching and landing of a projectile. And it goes through all the steps that we did some of in class as well today. So here's the problem statement. So imagine that you're on the top of a 15-meter tall building, let's say, and that you're launching a projectile at an angle of 30 degrees above the horizontal. As you can see, this launcher here is angled 30 degrees above. This angle from the horizontal is 30 degrees. And the initial speed of the object, which is this little ball here, is 10 meters per second. All right, so the goal here is to determine the time until this object hits the ground, and also the distance from the base of the cliff at which the object is going to hit the ground. And then finally, kind of like on the homework, I'm going to ask you to determine the object's final speed and angle of impact. So the first thing you're going to want to do is break apart the initial velocity vector, that's this blue arrow here, into both its x component and its y component. So once you do that, you can then look at just the vertical motion using the y component and the horizontal motion using the x component, using the kinematics equations that we already know. So since the angle is 30 degrees, this angle here, the x component is 10 times the cosine of 30 degrees, or 8.66 meters per second, and the y component is 5 meters per second. So what this means then is that as far as the vertical motion is concerned, this object, it's as if this object were thrown up with an upward velocity of 5 meters per second. And that's what we're interested in terms of determining how long it takes the object to hit the ground. And I did this example in class also, as I mentioned. So I'm going to plug in the values I know into the the free fall y kinematics equation that's given here. And I know that my initial height is 15 meters. My initial y velocity, this is important, is the 5 meters per second that we found out on the last slide. And of course, g I'm going to take to be 10 meters per second squared. So this is the quadratic equation that results from that. And if I factor out 5, I'll end up with this revised quadratic equation here, which I will then plug into the quadratic equation, and you can do that, and you'll get 2.3 seconds to be the time that'll satisfy this equation. So that's how long it's going to take this object to hit the ground given the conditions that I mentioned. So during those 2.3 seconds, remember the object is tracing out a trajectory that looks something like this. This is a little rough, of course, because I drew it by hand. But this is the path that the object is going to follow as it comes down to hit the ground. And it's moving with an x velocity of 8.66 meters per second, and that's not changing. So I can tell how far it's going to move by multiplying that 8.66 meters per second by the time it takes, the 2.3 seconds, and that's going to give me the 20-meter distance here. So that's the first two parts of the problem have now been answered. So now I'm interested in figuring out or determining what is the angle and the direction of the final velocity of the object. And remember, the final velocity is, if I go back to the previous slide, it's the velocity of the object right here, right before it's about to land. Notice that it has both an x component, which is the 8.66 meters per second, because that doesn't change. And it also has the y component. And the y component, it started off at 5 meters per second at the beginning, but it changes. And I can calculate what its new y velocity is going to be with this equation here. It's equal to the initial y velocity minus g times time. That's just the kinematics equations that we use for free fall motion for y velocity that we learned earlier in the semester. So the initial velocity of 5 meters per second minus g times time is going to give me 5 minus 23, or minus 18 meters per second. So in the y direction, right before it lands, it's going to be moving downward at 18 meters per second, in the x direction, 8.66 meters per second to the right. So I can figure out, these are the two components of the final velocity vector. So I can figure out the size of the velocity vector simply by using Pythagorean's theorem. It turns out that it gives me almost exactly 20 meters per second for the length of this vector here. The angle of this vector is important to know. What's the angle if you're playing baseball or something like that? You'd want to know what angle to hold your mitt so that you catch the ball. And so that's what this angle represents. And so I use SOHCAHTOA again. This angle here is the inverse tangent of the opposite side, which is 8.66 meters per second, divided by the adjacent side of this angle theta, which is 18 meters per second. So if I calculate that, that gives me 26 degrees from the vertical. So that's this angle here is 26 degrees. Or if you'd rather measure the angle from the horizontal, which is this where I'm pointing the arrow here, that's the horizontal direction to the arrow, that would be 74 degrees. So now we've taken care of this entire problem. And so you should be ready to approach the homework problem. The only thing I didn't do, and I'll leave that to you, is to figure out the maximum height of the projectile and where that maximum height is reached. Notice the other thing I could do with this projectile also is I could have angled it downward at some angle. The only difference to this problem would be that my initial y velocity in that case, if it was angled downward, would have a negative sign tied to it. The initial x velocity would still be positive x because it's moving in the right towards the right. Okay, hope this helps you.